What does capital P stand for? Pressure. Do you remember the standard SI units for pressure? Those are... Okay. Now, atmospheres are a kind of ordinary unit for pressure, but they're not the SI units for pressure.
Pascal.
There you go. Very good. That's right. The SI unit for pressure is pascals. What does capital V stand for? All right, now here's another unit question. Do you remember what the standard SI units are for volume? This is one that people usually get wrong.
I know it's not meters.
There you go. You're halfway there.
It's meters cubed.
That's good. That's right. Cubic meters. It's true that in chemistry it would be typical to use liters, but that's not the SI unit. If you think about it, we know that the SI unit for distance is meters. So for area, it should be square meters. So for volume, it should be cubic meters. So we're going to use cubic meters here. So let's say we're going from 3 cubic meters here to 7 cubic meters. So here we have another process where we're going from an initial to a final point. So let's calculate the work. Now notice that what is the work? It's the area under the PV curve. Now all of the previous examples I gave you, it wasn't obvious what the area was because they were complicated shapes. All the previous areas were things like this. Things with curved sides. Well, we don't have good techniques for finding the area of something with a curved side, at least not a simple technique. But it shouldn't be too hard to find this area. How would we find this area under the curve?
It's a square, so you just multiply both sides. And horizontally it's 5, and then vertically it's also 5. So
Take your time. What's the horizontal distance?
Oh, 4.
Okay.
It's 4.
There we go. Okay. Okay, so let's to review. What's the horizontal distance?
4.
And the vertical distance?
5.
Okay. And so this is a rectangle, and we know how to find the area of that. So what would the area be?
20.
20. Good. So our area here would be 20. So what's the work?
The work.
What number, what's the numerical value for the work? Well, remember that the work is the area. The work is the area under the curve.
And the work is being done by the gas, so it's a negative 20.
Now, that depends on which of these two definitions you're using. The work, so yeah, so in this case, is work being done by or on the gas?
By.
So the work done by the gas is just positive 20.
Okay.
What's the work done on the gas? That would be negative 20, because really work isn't being done on the gas. So if you wanted to focus on the work done on the gas, you'd have to say negative 20. But the work done by the gas is just a regular positive 20. As far as I'm concerned, it's probably easier just to focus on the work done by the gas, since that's what the gas is actually doing. It's doing work, so that's just a normal positive 20. Now, what are the standard units for work? Joules. We can be confident that this is going to come out in joules because we put in standard units. We put in pascals and cubic meters. Since we put in pascals and cubic meters, we can be confident this will come out in joules, even though we didn't work out step by step how that happened. Okay, so now we know that the work done by the gas here is 20 times, is 20 joules. So we've been saying that the work is the area under the PV curve, but a very simple case is when the PV curve is horizontal. When the PV curve is horizontal, then you can figure out the area pretty straightforwardly just by doing the height times the length. Let's figure out the work here. that's a good analysis. Work is being done on the gas, so the simplest thing would be to calculate the work done on the gas is 15. That's 5 times 3. The length is 5 and the height is 3. And then I would probably just plug into this formula. However, if you were really set on using this formula, then you would have to calculate the work done by the gas, which would be negative 15 joules. But the simplest thing is probably to calculate the work done on the gas and then use this formula. Good. Now, how about if we're not given the numbers, let's just get a general formula here. First thing to see is, remember that when is this a rectangle? When we have a horizontal PV curve. But what does it mean that this curve is horizontal? Well, what's happening to this gas? How would we describe what's happening to this gas qualitatively? What does it mean that this is horizontal and not upward or downward sloping?
The volume is, in this case, is increasing and the pressure is constant.
That's well put. That's exactly right. The volume is changing and the pressure is constant. Like you said, in this particular case, I happen to be showing the volume increasing, but I could also have shown the volume decreasing with the horizontal PV curve. The key thing is that if the PV curve is horizontal, the pressure is constant. So the last couple examples we've been doing have been constant pressure. Constant pressure. And then you just have a rectangle. And what's the height of the rectangle? And what's the length of the rectangle? Yep, that's well described. So doesn't this give us the general formula for constant pressure? If we have constant pressure, we're going to have a rectangle with a height of P and a width or a length of delta V. So this gives us the general formula for work when you have constant pressure. Now you have to label this as only for constant pressure, because if the pressure wasn't constant, we wouldn't have a rectangle, and we couldn't use this formula. This is only the work for constant pressure. And I haven't bothered saying whether this is work done on or by. That depends on whether you're expanding or contracting. So maybe we should just say, this will give you the magnitude of the work. This formula, remember I like to use dots to indicate magnitude. So we can put in the dots to show that this just gives us the magnitudes, and then you can decide on your own whether you should be focusing on the work done on or by the gas. But the magnitude of the work indicated by the dot is P times the magnitude of the change in the volume when you have constant pressure. Again, we wouldn't want to use this equation for this situation, because then it wouldn't be a rectangle. This is only for this case. In fact, what we're going to do now, maybe for the rest of the day, is it turns out there's many special cases for when you're working with the ideal gas law. You might have heard some of the special cases. Isothermal, adiabatic, constant volume, constant pressure. So we need to go into each of the special cases and see what are the special points about those. Well, now we've gone through our first special case, which is constant pressure. And you probably are going to be tested on the names for the cases. So we need to know what the name is for constant pressure. Well, what's a good prefix for constant, or things that are the same? A good prefix for constant or the same is iso. If you think of an isosceles triangle, that has two sides that are the same. So iso, or if you think about isotopes, isotopes are elements with the same number of protons. So iso means the same or constant. And I don't know if you've learned what is the device that people use for measuring pressure. You might have heard this on the weather report. What people use for measuring pressure is barometers. So another root for pressure is bar. So that gives us the name isobaric, means constant pressure. Just as a memory aid, if you remember that a barometer measures pressure, then you might that might help you to remember that isobaric means constant pressure. You might actually be tested on these names, so you should know that isobaric means constant pressure. And what's the most important thing to say to yourself if you see that you have an isobaric process? Well, first of all, what is the PV curve going to look like for an isobaric process?
Straight line.
Yeah, it's going to be a horizontal line. Not just a straight line, but a horizontal line. And what's the work going to be? Then it'll just be P delta V, because that's the area of the rectangle. So that's an important thing to learn about isobaric processes.
For the equation, in this case there's an increase in volume, so the volume is a positive value. If there was a decrease in volume, would I add the negative sign when I'm multiplying it by pressure, or would I just...
Are you talking about this case? Or,
well, like in the isobaric case, yeah.
Yeah. Well, again, these dots are to indicate that these are just magnitudes. We would just plug in the magnitudes.
Okay.
And then you would figure out the sign based on whether work was being done on or by the gas, and whether you were using this equation or this equation.